Welcome to the Sleepy Scientist. I'm glad you're here. Whether you're drifting off, winding down, or just looking for a quiet companion to keep you company, you've come to the right place. Before we begin, I'd love to know, where in the world are you listening from tonight? Are you bundled up in bed, or maybe curled into a quiet corner of the couch? Wherever you are, I hope you're comfortable, relaxed, and ready to explore something quietly extraordinary. And if you find these gentle journeys through science soothing or interesting, or even just oddly specific, please consider giving this video a like and subscribing to the channel. It helps more sleepy minds find their way here. And to those of you who've already subscribed, thank you. You're the gravitational core holding this whole sleepy galaxy together. Now, I'll do my best not to make this too fascinating, but if you do end up staying awake, at least you might learn a little something about the universe before you drift off. Tonight we're following a question so large, so quiet, and so strange that it almost seems like something out of a dream. Can two black holes become one? They begin far apart, separated by light years, but gravity has a plan. One day they'll spiral toward each other, not with fury, but with a quiet inevitability. No sound, no light, just the slow, relentless curve of space-time pulling them closer. Black holes are the most enigmatic objects in the universe. They defy our instincts, stretch the limits of physics, and seem to operate on the edge of what we can know. They're not holes at all, really, but rather places where gravity becomes so strong that even light can't escape. And yet, they're not malevolent or monstrous. They simply are. Still, patient, powerful, and despite their silence, black holes have a story to tell. A story written not in words or light, but in gravity, unfolding slowly across the vast canvas of the cosmos. In this video, we'll follow the tale of two black holes. We'll explore how they form, how they drift through space, and how, under the right conditions, they can find one another. Slowly at first, as if noticing each other across an unimaginable distance. Then with increasing urgency, as gravity draws them into a spiral, a dance that could last millions or even billions of years, until finally they merge into one. This isn't science fiction, it's science. And not only has this happened, many times in fact, but we've also found a way to hear it. With the help of gravitational wave observatories, scientists have listened to the final moments of black holes colliding. These ripples in space-time, so faint they're smaller than a proton, carry with them stories of immense power, quiet collisions, and the invisible forces that shape the universe. But before we get there, we'll slow things down. We'll take our time. Because this story isn't just about the physics of collision. It's about the poetry of gravity, the way it brings things together, the way it bends the rules of space and time, the way two dead stars, long forgotten by the light, can create something new by falling into each other. We'll look at how black holes form, how they affect the space around them, and how they shape entire galaxies. We'll drift through the quiet chaos of the early universe, where black holes may have seeded the very structure of everything we see today, and we'll explore what happens when two of these objects meet, what they leave behind, and what we might learn from the echoes of their union. You don't need to remember equations, you don't need to stay awake for every moment, just let the ideas float past like stardust. There will be gravity to catch them. And so, let's begin. Let's follow two black holes on a journey through space and time, a journey billions of years in the making. What happens when they meet? What do they become? And how does the universe remember it? In the quiet darkness of the cosmos, there are places where the rules change, places where time slows, space bends, and the ordinary becomes impossible. These places are not made of matter, not in the way we usually think of it. They are not solid, not gaseous, not even empty. They are black holes, regions of space where gravity has taken control so completely that nothing, not even light, can find a way out. To understand what a black hole is, we need to look at how stars live and die. Most stars, like our Sun, shine for billions of years, fueled by the nuclear fusion of hydrogen into helium deep in their cores. This fusion pushes outward, creating a delicate balance against the inward pull of gravity. It's a cosmic standoff that defines a star's life, but eventually the fuel runs out, and when it does, gravity wins. For small and medium-sized stars, the end is relatively peaceful. They shed their outer layers and fade into white dwarfs, dense glowing remnants that cool slowly over time. But for very massive stars, those more than about 20 times the mass of our Sun, the finale is far more dramatic. When these giants run out of fuel, they collapse under their own weight in an instant, triggering a supernova, one of the most powerful explosions in the universe. What's left behind after the blast depends on just how massive the core is. Sometimes it becomes a neutron star, a city-sized object so dense that a single teaspoon would weigh billions of tons. But if the core is heavy enough, not even neutron pressure can stop the collapse. It keeps going past atoms, past protons, into a point of no return. And that's when a black hole is born. But what exactly is a black hole? Is it a thing? A place? A hole? In truth, a black hole isn't an object in the traditional sense. It's more like a region, an area of space where gravity has become absolute. At its boundary lies the event horizon. This is not a wall or a surface you could touch. It's simply the distance from the center of the black hole at which escape is no longer possible. Cross that line, and no matter how fast you travel, even at the speed of the light, you can't get out. The name black hole is fitting, not because it sucks things in like a vacuum cleaner, but because once something crosses the event horizon, it can no longer send any information back. No light, no sound, no signal. It disappears from the visible universe, leaving behind only its gravitational signature. In that sense, black holes are more like cosmic secrets, hidden chapters in the book of the universe, closed and unreadable. At the very center of a black hole, if the equations are to be believed, lies the singularity. This is a point where the known laws of physics break down, where density becomes infinite, and time itself may cease to function in any meaningful way. It's not that we know what happens at the singularity, we don't. It's that our theories can no longer describe it. General relativity reaches its limit there, and quantum mechanics has yet to step in with a complete answer. The singularity is not a place we can visit or observe. It's more of a question mark than a period. From the outside, black holes don't look especially dramatic. They're perfectly spherical, completely dark and featureless, but their gravitational pull is immense. Get close enough, and even light itself bends around them. This effect, known as gravitational lensing, allows astronomers to detect black holes indirectly, by observing the way their presence distorts the light of stars and galaxies behind them. Some black holes are small, just a few times the mass of the Sun. These are known as stellar mass black holes, and they likely form in great numbers throughout the universe. Others are far larger, millions or even billions of times the Sun's mass. These are supermassive black holes, found at the centers of galaxies, including our own Milky Way. And in between, we're still searching for evidence of intermediate mass black holes, the cosmic middle children that could fill the gap in our understanding. But regardless of size, the defining trait of a black hole remains the same. Once you cross its event horizon, you're no longer part of the observable universe. You become part of something else, something silent, something final. There's a strange kind of beauty in that. Black holes are not chaotic storms or exploding stars. They are the leftovers of immense energy, frozen in silence. They do not announce themselves with noise or fury. They simply curve space so deeply that the rest of the universe falls inward, slowly and without resistance. Even now, scientists are still learning how these strange regions behave. New telescopes, like the Event Horizon Telescope, have begun to image the shadows cast by black holes. Instruments like LIGO and Virgo have detected the gravitational whispers of black holes colliding, And yet, with all this progress, black holes remain deeply mysterious, part physical reality, part philosophical puzzle. They are a natural consequence of gravity taken to its extreme. They are inevitable in a universe that allows stars to die and time to bend. And they remind us that even the most familiar laws, like the way objects fall or how light travels, can break down under the right conditions. To understand black holes is to understand the extremes of nature. They are not an exception to the rules. They are the rules, pushed until they crack. And though they may seem distant or abstract, they shape galaxies, alter the flow of time, and leave echoes across the fabric of space. In their silence, they speak of something deeper, something both terrifying and beautiful. The universe, folding in on itself. Gravity is something we live with every day. It's the quiet reason our feet stay on the ground, why apples fall from trees, and why the moon never drifts away. It's familiar, gentle, constant. But in the deeper corners of the universe, gravity becomes something stranger, something so powerful and so warped that it begins to defy our common sense. Nowhere is this more true than with black holes, where gravity doesn't just pull, it transforms reality. To appreciate just how unusual black holes are, it helps to understand gravity as we first came to know it. For centuries, we saw it through the lens of Isaac Newton, who imagined gravity as a force, an invisible thread stretching between masses, pulling them toward one another. According to Newton, everything with mass pulls on everything else. The more mass an object has and the closer you are to it, the stronger the pull. Simple, elegant. And for most of the universe, this idea works beautifully. It's why Earth holds us in place, why the moon orbits the Earth, and why planets loop around the sun. But Newton's gravity treats space as a kind of static stage, a cosmic floor where objects perform their dance, tugging at each other across invisible gaps. But in the early 20th century, Albert Einstein offered a new idea, one that would change everything. Einstein proposed that gravity isn't really a force at all, but a curvature of space and time. Mass, he said, tells space how to bend, and space tells objects how to move. Imagine a trampoline stretched tight. If you place a bowling ball in the center, the fabric dips. Roll a marble across it, and the marble curves toward the ball, not because there's a string pulling it, but because the surface itself is warped. This was the insight of general relativity. Gravity is geometry. The more massive an object, the deeper the dent it makes in the fabric of space-time. Planets dip the sheet a little. Stars dip it more. But black holes punch a hole straight through it. What makes black holes gravitationally unique is not just how much mass they contain, it's how compact that mass is. Black hole isn't a big thing. In fact, for all its mass, it can be surprisingly small. A black hole with the mass of our sun would be only about 6 kilometers across. That's roughly the size of a city. All that matter, all that gravity squashed into something so tiny, it curves space-time into a funnel so steep, nothing can climb out. This leads to the idea of escape velocity, the speed you'd need to break free from an object's gravitational pull. Earth's escape velocity is around 11 kilometers per second. The sun's is more than 600 kilometers per second. But at the event horizon of a black hole, the escape velocity reaches the speed of light. And since nothing in the universe can travel faster than light, nothing can escape. Not even photons. Hence, the darkness. But what's truly mind-bending isn't just the steepness of the curve, it's what lies at the bottom. If you follow the math all the way in, past the event horizon, past the outer layers of twisted space-time, you eventually arrive at a singularity, a point of infinite density. Now, infinite is a word science usually tries to avoid. It's more of a flag that says, we don't know what's happening here. Infinite density means all the mass of the black hole is concentrated into a single point with no volume, an idea that breaks every rule we have. Physics, as we know it, cannot handle this. our equations collapse, space and time may cease to behave in any meaningful way. In a way, a black hole singularity is like a cosmic paradox. It's the end of our understanding, not because it's unknowable in principle, but because our current theories, relativity and quantum mechanics, don't work together well enough to describe it. Something better is needed. Some theory of quantum gravity that can explain what happens when immense mass meets microscopic scale. But from the outside, you'd never know any of this. Black holes don't look violent or chaotic. They're not whirlpools or swirling maelstroms. They're just there. Silent, dark, perfectly spherical. What gives them away is how they affect the things around them. Stars orbit too fast. Light bends in unexpected ways. Time slows down. And here's another strange twist. Gravity near a black hole doesn't just pull on matter, it pulls on time. According to Einstein's theory, time itself passes more slowly in stronger gravitational fields. Near the event horizon, clocks tick at a fraction of their normal speed. For someone watching from a distance, anything falling toward the black hole appears to slow down, taking longer and longer to reach the edge, until it seems to freeze just above the surface. Of course, from the perspective of the falling object, there's no freezing. It crosses the event horizon in a finite amount of time and keeps going, somewhere. But to an outside observer, it never quite gets there. Time, space, light, motion, they all get tangled up in the gravitational web. This warping of space and time is what sets black holes apart from every other object in the universe. They're not just heavy, they're concentrated in a way that twists the very fabric of reality. And while their influence is felt strongly near the event horizon, it extends far beyond. A black hole can anchor stars in orbit, distort the paths of nearby light, and alter the very structure of galaxies. And yet, for all their power, black holes obey the same laws as everything else. Their gravitational pull from afar is no different than any other object with the same mass. If the Sun were magically replaced by a black hole of equal mass, Earth's orbit wouldn't change. We'd just be a little colder. The gravity of black holes isn't about more. It's about deeper, not stronger but steeper, a plunge instead of a pull, a silence that hides the loudest truths in the universe. In the end, black holes remind us that gravity isn't merely a force, it's the shape of reality. And sometimes, that shape folds inward, vanishes from view, and leaves behind only the memory of what once was. Gravity so complete, it becomes nothing at all. Every black hole begins as a star, but not just any star. Its story starts in a cradle of dust and gas, a glowing, swirling cloud known as a nebula. These clouds float silently through the galaxy, vast and cold, until something disturbs them. A passing shockwave, perhaps from a nearby supernova, ripples through the gas and triggers a slow collapse. Gravity begins its quiet work, pulling atoms closer and closer, clumping hydrogen into tighter knots. As the gas collapses inward, pressure builds. In the heart of the cloud, the material becomes so hot and dense that hydrogen atoms begin to fuse. They join to form helium, releasing tremendous energy in the process. A new star is born, its core burning steadily, shining outward with light and heat. This fusion releases enough outward pressure to balance the inward pull of gravity, creating a fragile equilibrium, and for a time, sometimes millions, sometimes billions of years, that balance holds. Massive stars burn hot and bright, living fast compared to their smaller siblings. A star like our Sun can live for more than 10 billion years, but a star with 20 or 30 times the Sun's mass might last only a few million. Their cores are furnaces of unimaginable heat, fusing heavier and heavier elements in sequence, hydrogen into helium, helium into carbon, carbon into oxygen, and so on. Layer by layer, they build an onion-like structure of burning shells, each fusing a different element into something heavier. Eventually the core produces iron, and that's when the process grinds to a halt. Iron doesn't yield energy when fused. In fact, fusing iron consumes energy instead of releasing it. Once a star's core becomes iron, fusion can no longer support the star's weight. The outward pressure that held gravity at bay vanishes, and the star collapses inward at incredible speed. This collapse happens in seconds. The core implodes, atoms are crushed, protons and electrons merge into neutrons, and the outer layers rebound off the compressed center, triggering a massive explosion, a supernova. For a brief moment, the star outshines entire galaxies. Its light races across space, carrying news of its death to the wider cosmos. What remains at the heart of this cataclysm depends on how much mass was left in the core. If the core is between about 1.5 and 3 times the mass of the Sun, it becomes a neutron star, a dense ball of matter no wider than a city. In a neutron star, gravity is strong enough to crush atoms, but not strong enough to create a black hole. These stars are extraordinary in their own right. A teaspoon of neutron star material would weigh billions of tons. But if the core is too massive, even neutron pressure can't save it. Gravity continues its collapse. Nothing resists it. No force in the universe is strong enough to stop what comes next. The core contracts beyond the point of any known structure, compressing into an infinitely dense point, a singularity. A black hole is born, and with it, an event horizon, the invisible boundary that marks the edge of no return. From the outside, the transformation is silent. There's no flash or ripple. The matter vanishes from sight, wrapped in a cloak of darkness. What was once a star has now become a region of space defined only by mass, spin, and charge. No surface, no features, just gravity. This is the fate of only the most massive stars, those with enough material to tip the scales beyond what nature can resist. Lesser stars, even those larger than our Sun, will never reach this end. They will live long, gentle lives, shedding their outer layers to form planetary nebulae and leaving behind white dwarfs, dense but stable, glowing slowly into obscurity. But the titans burn fast and die young. Their lives are measured in millions, not billions of years, and when their fuel runs dry, they don't fade. They collapse with unstoppable force. Their deaths seed the universe with heavy elements, gold, platinum, uranium, created in the chaos of their final moments. These elements drift through space, settle in new clouds, and eventually become the building blocks of planets, people, and everything we know. In that way, the death of massive stars is both an end and a beginning. It is destructive and creative, violent and necessary. Without these stellar deaths, there would be no carbon for life, no iron for blood, no silicon for bones. And so, black holes are born not in isolation, but as part of the grand cycle of matter. They are the final act in the story of certain stars, written not in fire, but in collapse. They are what's left behind when gravity wins completely, when the fabric of space folds inward and says no more. It's tempting to think of black holes as exotic or rare, but they may be scattered throughout our galaxy in the thousands, hiding quietly in the dark. Each one was once a star, bright and burning, part of a constellation, perhaps even with planets circling it. Now they are invisible monuments to gravity's power, a story that ends not with a bang, but with silence. And though they no longer shine, their presence can still be felt. Their pull shapes the motion of nearby stars. Their influence warps the paths of light. They linger like ghosts in the galaxy, not gone, but transformed. A reminder that even the mightiest stars can fall, and in doing so, create something stranger than fiction. This is how black holes come to be, not as invaders or monsters, but as natural products of stellar evolution. They are what happens when mass is compressed beyond the limits of light, when the fire goes out and gravity whispers, "Come closer." Imagine space not as an empty stage, but as something soft, something that can bend, stretch, and ripple. Picture a vast rubber sheet stretched tight, Place a bowling ball in the middle and the sheet dips. Now roll a marble across the surface. As it approaches the dip, its path curves. Not because it was pulled exactly, but because the very surface it's moving across has changed shape. This is how Einstein reimagined gravity. In his theory of general relativity, space and time are woven together into a single fabric, space-time. And this fabric isn't fixed or flat. It bends in response to mass and energy. The more massive an object, the deeper the curve. The Earth makes a small dent, the Sun a deeper one. But a black hole doesn't just dip the fabric, it punches a hole straight through. This warping is what gives gravity its power. Objects aren't being tugged by invisible threads. They're simply following the curves of space-time. When you toss a ball, it travels in a straight line, but through a space that is itself curved. The ball's path bends because the space it moves through bends. And where the fabric is curved most deeply, time itself begins to behave strangely. One of the most fascinating predictions of relativity is time dilation. The idea that time moves at different rates depending on how close you are to a massive object. Near a black hole, this effect becomes extreme. Clocks tick more slowly, seconds stretch out, minutes take longer to pass. If you were hovering safely near a black hole's event horizon, you might feel like only a few hours had gone by. But for someone watching from far away, years could have passed. This isn't science fiction, it's measurable. We've confirmed time dilation with satellites and atomic clocks. GPS systems even have to account for it to give you accurate directions. But near a black hole, the effect is far more dramatic. If you could somehow survive the journey, you might return to find the universe aged beyond recognition, while you'd barely aged at all. Time and space are not separate fixed dimensions. They are part of the same flexible continuum, and gravity bends them both. Now let's talk about light. Light, like any other traveller, follows the curves of space-time. When it passes near a massive object, its path bends. This bending is called gravitational lensing, and it allows us to see black holes indirectly. Imagine a star shining behind a black hole. The light from that star curves around the black hole's gravity, creating arcs, rings, or even duplicate images. These distortions are not just pretty, they're evidence. They tell us how much mass is there, even if we can't see the source directly. It's a cosmic fingerprint left by an object that doesn't reflect light at all. Some of the most beautiful images captured by telescopes, those graceful, stretched out smears of galaxies and stars, are the result of gravitational lensing. And in rare cases, this lensing can create what's known as an Einstein ring, where the background light wraps into a full circle around the invisible object in front. It's like the universe is drawing a glowing halo around a hole in space. The stronger the gravity, the more extreme these effects become. Near a black hole, space-time is so severely curved that light can orbit it. There's a region just outside the event horizon called the photon sphere. Here, photons, particles of light, can circle the black hole endlessly, caught in a perpetual gravitational loop. Any deviation, even the smallest nudge, sends them spiraling inward or flinging back out. From a distance, a black hole doesn't look like a hole. What we see is its shadow, the absence of light, surrounded by a bright distorted glow from the material around it. This is what the Event Horizon Telescope captured in 2019, when it revealed the first image of a black hole silhouette. Not the black hole itself, but the shape it carves into the light around it. That image wasn't just a scientific achievement, it was a glimpse at warped reality. A portrait of space twisted in on itself. To exist near a black hole is to live in a universe where directions lose their meaning. Where down becomes toward the singularity, and time becomes stretched and strange. Space curves so sharply that moving in what feels like a straight line might bring you back to where you started, or send you across space in an unexpected arc. Time slows, light bends, and reality feels more like a dream than a map. But here's the astonishing part. This isn't just theoretical. These predictions, drawn from equations written over a century ago, have been confirmed by observations again and again. from the bending of starlight during an eclipse, to the red shift of light escaping massive galaxies, to the precise dance of orbiting stars near the centre of our own Milky Way, all of it supports the idea that gravity isn't a force, but a shape. Black holes take that shape to its limit. They are not just heavy objects, they are events in space-time. They are regions where the curvature becomes so intense that the fabric folds inward and seals itself off. The closer you get to a black hole, the stranger the world becomes. A beam of light curves like a river. A second becomes a century. The geometry of everything stretches and twists until familiar rules begin to fail. And yet, the laws of physics hold. They bend, but they don't break. The same rules that govern an apple falling from a tree also govern the bending of galaxies around black holes. The difference is only one of scale. When we look at black holes, we are seeing the edge of what space and time can do. They are nature's way of showing us that the universe is not a rigid machine, but a flexible, flowing thing, one that curves and bends and warps with grace and mystery. In their silence, black holes remind us that gravity is not a shout, but a whisper, a subtle reshaping of reality, hiding just beneath the surface of what we think we understand. In the great quiet of space, even black holes can find companions. Though it may take millions or even billions of years, gravity has a way of bringing things together. And when it comes to black holes, that coming together is not sudden. It begins with a slow, spiraling dance, graceful, precise, and strangely beautiful. Imagine two black holes drifting through the galaxy. Each is invisible, but their gravity tugs gently at nearby stars and gas, betraying their presence. Perhaps they formed separately, remnants of different massive stars in a dense star cluster. Or perhaps they were born within the same collapsing cloud, siblings destined for reunion. Either way, if they pass close enough, their immense gravitational fields begin to interact. At first, they might orbit loosely, at great distance, circling each other like shy dancers across a vast floor. Their movements are dictated entirely by gravity. There is no friction in the vacuum of space, no ropes or magnets pulling them together, just the mutual attraction between 2 points of incredible mass, locked in a shared geometry. Over time, their orbits become tighter. This is not because something is pushing them, rather the system is losing energy. With every pass, the two black holes radiate a faint tremor into the fabric of space itself, a ripple known as a gravitational wave. Gravitational waves are not sound, they are not light. They are distortions in space-time itself, spreading outward in all directions like ripples on a still pond. These waves carry energy away from the system, and as energy is lost, the black holes move ever so slightly closer together. Their orbit shrinks, their pace quickens. This process, called in spiral, can last for eons. In the early stages, the loss of energy is almost imperceptible. The gravitational waves are too faint to detect, and the orbit's too wide to change quickly, but the process is relentless. Slowly, quietly, the black holes spiral inward, round after round, like clocks ticking toward a final hour. As they draw closer, their speeds increase. By the time they are only a few orbits away from each other, they are moving at a significant fraction of the speed of light. Imagine two invisible objects, each the mass of several suns, circling one another dozens of times per second, in a gravitational embrace that is tightening by the moment. The energy released in those final stages is staggering. For a brief instant, just before they merge, the system can emit more power in gravitational waves than all the stars in the observable universe emit in light. And yet, this outburst is silent. Unless you were a gravitational wave detector, you would never notice. No flash, no sound, no sign. Just a shiver in the fabric of space, passing quietly through the cosmos. It's easy to imagine these black holes as active, aggressive objects pulling toward each other with fury. But their union is not a collision in the explosive sense. It's a slow convergence, dictated by the laws of general relativity. Even in their final seconds, they follow curved paths, spiraling ever faster, ever closer, until the moment of merger. But let's step back to the earlier phases where the process truly begins. Often these black hole pairs are found in dynamic environments, crowded places like globular clusters or the cores of merging galaxies. In such places, stars and remnants jostle and collide, and black holes can sink toward the center through a process called dynamical friction. This friction isn't like rubbing your hands together. It's the gravitational interaction between the black holes and the sea of surrounding stars. As a black hole moves through the cluster, it creates a wake of disturbed stars behind it, and this wake tugs back, slowing it down. Over time, this causes the black hole to spiral inward, increasing the chances that it will meet another. Once two black holes form a binary system, gravitationally bound to one another, they are locked in a long-term relationship. Their dance becomes the dominant feature of their region of space. Nearby stars can be ejected as the pair slingshots them away, a process known as the gravitational slingshot. In fact, many binaries harden over time by interacting with these passers-by, trading energy for momentum and tightening their orbits even before gravitational waves begin to dominate. Eventually, gravitational radiation takes over as the primary driver of orbital decay. Though these waves are incredibly weak and difficult to detect, their effects are real and cumulative. Over millions of years, they carry away the angular momentum of the system, like a gentle but persistent tide. The orbit becomes smaller, faster, more elliptical, and finally, in the last few minutes, it transforms into a near-circular death spiral. From our vantage point on Earth, these final orbits produce a telltale signal, a rising chirp in the data, as the frequency and amplitude of gravitational waves increase together. That chirp tells us a story of motion, of decay, of two invisible giants circling toward a single point in space. It's a strange thought that the most violent events in the universe begin so quietly, that the collapse of time and space starts with nothing more than a slow turn, an imperceptible drift. But that is the nature of black holes. They do not crash like cymbals. They hum and whisper and draw close with perfect timing. As they spiral inward, they carry with them the memory of all that came before, the stars that collapsed, the space they moved through, the paths they took to find each other. Their orbits are not random. They are stories, written in gravity, read by the careful instruments we build to listen. And though we often speak of black holes as mysterious or unknowable, the truth is their movements are governed by some of the most well-understood equations in physics. Their orbits follow predictable paths. Their loss of energy matches precise calculations. Even the waves they emit can be modelled and traced. Still, there's something poetic in the idea of two objects, born from the ashes of stars, slowly finding each other across the gulf of space. Drawn together by nothing more than gravity and time, their orbits decay not because they fail, but because they succeed. They have no resistance, they follow the curve of space-time perfectly, until there is no curve left to follow, just a single point, a single horizon, and the merging of two into one. In the grand quiet of the cosmos, black holes don't often travel alone. While they are solitary by nature, mute, invisible, and all-consuming, the universe has a way of drawing them together. Through long, patient processes, woven across millions or billions of years, black holes can find one another. Their meeting isn't sudden or romantic, but it is inevitable, sculpted by gravity and chance. Picture a globular cluster, one of the oldest and densest environments in the galaxy. These clusters are like stellar cities, each home to hundreds of thousands of stars packed into a space just a few dozen light-years wide. The stars here drift like bees in a slow-motion swarm, jostling and tugging on one another through gravity alone. Some of these stars are long gone, their cores collapsed into black holes. Others are still shining, slowly aging. In such crowded spaces, chance encounters are common. And when it comes to black holes, a few close passes can lead to something more lasting. Over time, black holes within globular clusters tend to sink toward the center. This happens because of a process known as mass segregation. Heavier objects naturally drift inward as lighter ones migrate outward. The result is a sort of cosmic sorting. Dense remnants, including neutron stars and black holes, gather in the core. There, they orbit among each other in tight loops, bumping and scattering like marbles in a bowl. Every close interaction has the potential to bind two black holes together into a binary, a gravitational partnership that may last for eons. Some of these pairs are short-lived, others are stable enough to begin the slow dance of in-spiral, and in the densest regions of the cluster, gravitational slingshots, where one black hole flings another out in exchange for tighter orbits, can accelerate the process. It's a gravitational game of billiards, played across cosmic distances and unimaginable timescales. But not all black holes meet in clusters. Some are born into binary systems right from the start. Massive stars often form in pairs. In fact, astronomers believe that most massive stars, those destined to end as black holes, are born with a companion. These binary stars orbit each other closely, sharing their lives from their earliest moments. As each evolves, their relationship changes. One star may swell into a red giant, transferring mass to its partner. Eventually, one collapses into a black hole, leaving behind a dark, silent companion. If the system survives this explosive transition, the second star may follow the same path. And when it does, you're left with two black holes orbiting each other from birth, their fate already sealed. These stellar origin black hole binaries are some of the best candidates for eventual mergers. Their orbits may start wide, but over millions of years, gravitational waves carry energy away, tightening the spiral. By the time they reach the final moments, their motion can be detected from billions of light years away. And then there are the giant stages, environments not just crowded with stars, but with entire galaxies. Galaxies do not stay still. They move, drift, and collide. Over cosmic time, galaxies are constantly merging, small ones being swallowed by large ones crashing together to form even grander structures. And at the heart of nearly every galaxy lies a supermassive black hole, millions or even billions of times the mass of the Sun. When two galaxies collide, their stars almost never hit each other directly. The space between stars is so vast that they mostly pass through unharmed. But their gravitational fields mingle, tugging stars into new orbits, stirring up gas and dust, and setting off waves of star formation. And deep within the chaos, the supermassive black holes at the cores of both galaxies begin to drift toward each other. At first, their movement is slow and uncertain. They spiral inward over hundreds of millions of years, nudged by the gravity of passing stars and clouds of gas. As they grow closer, they may form a binary, two invisible giants orbiting one another at the center of the newly formed galaxy. In time, they too will merge, unleashing an unimaginably powerful wave of energy into the fabric of space-time. These titanic mergers are thought to shape galaxies themselves. The resulting black hole is larger, more energetic, and often spinning rapidly. Its gravity helps regulate star formation in the surrounding galaxy by heating or expelling gas. In this way, black hole mergers are not just endings. They're part of a creative process that sculpts the universe on the larger scales. Even far from galactic centers, black holes can be drawn together by sheer numbers. In star-forming regions where dozens of massive stars are born together in clusters, many will eventually collapse into black holes. Over time, their mutual gravity pulls them inward, leading to close encounters and the occasional pairing. The result is a quiet network of black holes, spiraling through the galaxy, some destined to meet. But for all their mass and influence, black holes don't actively seek one another. They don't move through space with purpose. They drift, they fall, and sometimes they find themselves caught in a gravitational tug-of-war that brings them closer to another just like them. Whether born as a binary, formed in a chaotic cluster or nudged together by the merger of galaxies, the result is the same, a partnership defined by gravity and time. What makes this process so compelling is how unhurried it is. There's no rush. Two black holes might circle each other for billions of years, slowly spiraling inward with no witness, no sound, and no resistance. Their eventual union is a consequence of persistence, not force. And across the universe, these stories are unfolding all the time, in the dark centers of galaxies, in the crowded hearts of star clusters, in the quiet trails left behind by ancient stars. Each black hole merger begins with a meeting, a delicate moment when gravity decides that two paths, once separate, will now bend toward each other forever. The universe does not stage these encounters with drama or noise. It simply allows them. Over vast distances and endless time, gravity draws black holes together, not because it must, but because it can. In the silence between the stars, even the most unlikely pairs can find one another. In the cold and empty stretches of space, the final act begins in silence. Two black holes, once drifting alone, have found each other. Their orbits have tightened over millions, perhaps billions of years, each revolution drawing them a little closer, each moment releasing just a whisper of gravitational energy. They move faster now, circling hundreds of times per second, sweeping through space-time like invisible whirlwinds. At this stage, their separation is no more than a few times the diameter of their event horizons. Their individual identities begin to blur. From afar, they are no longer two distinct objects, but a single system. A pair of immense masses dancing in lockstep, radiating energy in ripples that stretch across the universe. This is the final inspiral, a breathtaking and brief moment when the decay of the orbit accelerates rapidly. Every time they loop around one another, they lose energy to gravitational waves. Those waves ripple out from the system, flattening and stretching space in alternating pulses. They do not travel through space as light does. They are changes in space, expansions and contractions that pass through matter like it isn't even there. And while we can now detect these waves with extraordinary precision, they carry only the tiniest fraction of their energy toward us. The vast majority of that energy remains in the warped region of space-time around the black holes themselves. Their orbits shrink by kilometers with each pass. The frequency of their gravitational waves rises. The amplitude swells. The system begins to sing. Then comes the plunge. The moment of collision is not like a crash between two cars. There is no noise, no shattering of matter, no sparks or flying debris. There may be no matter at all, just two curved regions of space-time rushing toward a common center. As their horizons touch, they merge into a single larger black hole. No sharp boundary, no flash. One becomes two, then becomes one again. If any gas or dust remains nearby, it may light up briefly, heated by the tremendous gravitational energy released in the final moments. But in many cases, especially with isolated stellar mass black holes, there is little or no matter left. The merger is dark. All that escapes is gravity, encoded in those rippling waves, now spreading outward in all directions. At the moment of union, the new black hole is not quite settled. It quivers, like a struck bell, vibrating with leftover energy. This stage is known as the ring down. The newborn black hole is distorted, its surface briefly wobbling with intense gravitational tension. These distortions quickly dampen, radiating away as more gravitational waves until the shape becomes smooth and stable. The result is a perfectly quiet, perfectly spherical, spinning black hole. That final ringing signature, the gravitational echo of the merger, is one of the clearest clues to what just occurred. From it, physicists can extract precise information. The masses of the original black holes, their spins, the distance of the merger, and the properties of the final object, all from a signal that may last only a fraction of a second. And yet, for all its brevity, that moment tells the story of an entire cosmic journey. The original stars that formed, lived, and died. the black holes that drifted and danced, the space-time that curved and twisted, and finally the transformation of two invisible objects into one. In these final stages, space-time behaves in ways that strain the limits of our understanding. The curvatures are extreme, so steep that even light cannot escape. Time slows dramatically. For an external observer, the merger appears to happen in slow motion, stretching toward infinity. But from the perspective of the black holes themselves, the union is quick, seamless, and absolute. Energy, too, takes on new meaning here. A significant portion of the system's total mass is radiated away as gravitational waves. In some cases, up to 10% of the mass is lost this way, converted not into light or heat, but into pure distortion of space-time. It's among the most efficient energy conversions in the universe, and yet it produces no light, no sound, no trace in any conventional sense. To put it into perspective, when the first gravitational wave was detected from a black hole merger in 2015, it came from a pair of black holes that merged over 1 billion light-years away. In that brief moment, they released more energy than the entire visible universe, yet the signal that reached Earth stretched our instruments by less than the width of a proton. The physics of merging black holes is rooted in Einstein's equations, but it also touches the edges of something more poetic. These mergers are not simply physical events, they are transformations. Two gravitational identities merge into one. Two curves in space-time become a single, deeper well. It's hard not to imagine the merger as a kind of cosmic breath. A slow, deep inhale over eons followed by a sudden exhale of gravitational energy, a sigh from the universe itself. What remains afterward is still, dark, and quiet. But the space-time around it remembers. The waves continue, moving outward forever, carrying with them the shape of a story that began with stars. We have only recently begun to detect these events, and yet already they've reshaped our view of the cosmos. They've revealed black holes we didn't expect, with masses and spins that challenge our models. They've proven that black holes do, in fact, collide, and they've given us a new way of listening to the universe, not through light, but through gravity itself. Each merger is a moment of clarity in an otherwise silent sky. A brief event that tells of ancient beginnings, violent endings, and a universe always in motion, always changing shape. And though the collision is invisible to the eye, its echo moves through everything, through galaxies and stardust, through the space between atoms, through us, a ripple born in the heart of nothing, reaching quietly across the stars. Imagine tossing a stone into a calm pond. Ripples spread outward in perfect circles, each one carrying a little energy away from the point of impact. Now, imagine a much stranger pond, the kind made not of water, but of space-time itself. In this invisible medium, a ripple doesn't just shake the surface, it stretches and squeezes the very fabric of reality. These are gravitational waves, silent messengers from the depths of the universe, born from motion, carrying whispers of cosmic events that would otherwise leave no trace. Gravitational waves were first predicted by Albert Einstein in 1916 as part of his general theory of relativity. According to Einstein, mass and energy bend space and time, and when massive objects accelerate, especially in asymmetrical ways, they send out ripples through that curved fabric. Think of two dancers holding hands and spinning. As they twirl, they disturb the floor beneath them. The faster they spin, and the more massive they are, the stronger the vibrations. But there's a catch. Gravity is incredibly weak compared to the other fundamental forces. You can overcome the gravity of the entire Earth just by lifting a cup of tea. So the ripples it produces, even from colossal events, are vanishingly faint. Einstein himself wasn't sure we'd ever be able to detect them. For a long time, they remained a beautiful but unreachable idea, like hearing the heartbeat of the cosmos, but from the other side of a wall. Then came black holes. Black holes are the ultimate engines for gravitational waves. They have no surfaces, no hair, no fuzz. just mass, spin, and charge. And when they orbit each other, their incredible mass and acceleration twist space-time in the most dramatic way imaginable. Two black holes spiraling toward one another don't just disturb their surroundings, they churn space-time itself, like spoons in cosmic syrup. When they finally merge, the ripples they produce travel outward in all directions, undisturbed, untouched, and almost perfectly clean. These ripples are different from light or sound. They don't bounce off things, they don't get absorbed by dust, and they don't fade in the way electromagnetic waves do. They stretch and compress space itself as they pass through it. If a gravitational wave were to pass through your body, the distance between your head and your toes would momentarily shrink and expand by a tiny amount, too small to notice, but real nonetheless. For decades, gravitational waves remained a theoretical prediction until something extraordinary happened. In the early 2010s, a pair of detectors, one in Washington state and another in Louisiana, were upgraded into a new system called LIGO, the Laser Interferometer Gravitational Wave Observatory. Using lasers, mirrors and arms 4 kilometers long, LIGO was designed to measure changes in length smaller than the width of a proton. It sounded impossible, and for a long time it looked like it might be. But then, in September of 2015, the instruments picked up a signal. It was a short, rising chirp lasting just a fraction of a second. That chirp came from two black holes more than 1 billion light-years away, merging into one. Their final few orbits had sent out gravitational waves that crossed the universe to reach Earth. And for the first time, humanity had heard the cosmos in a brand new way. Since then, dozens more black hole mergers have been detected, each with its own signature. Some come from massive black holes, others from lighter pairs. Some appear to be spinning. Each merger reveals something new, not just about black holes, but about the structure of space itself. The waves carry information unfiltered by gas or dust. They arrive in perfect timing. They're like telegrams from the deep past, still ringing out in the present. But why are black hole mergers so perfect for generating gravitational waves? It comes down to motion and mass. For gravitational waves to be strong enough to detect, you need objects that are both incredibly heavy and rapidly accelerating. Two black holes in a close orbit meet both conditions. They're compact so they can get very close together, and that closeness means they orbit quickly. In their final moments, they circle each other dozens or even hundreds of times per second. That kind of motion disturbs space-time in exactly the way needed to send ripples outward. There are other sources of gravitational waves too. Neutron star collisions, spinning pulsars, even supernovae. But black hole mergers are especially clean. Since they lack solid surfaces, there's no messy matter to muddle the signal. The waveform they produce is smooth, predictable, and beautiful. From start to finish, it tells a complete story. The slow in-spiral, the rising frequency, the peak at collision, and the soft ring down as the final black hole settles into shape. Gravitational wave astronomy is still in its infancy, but it's already transforming our understanding of the universe. It allows us to see things we could never detect before. Two black holes merging in the darkness of empty space, without emitting any light at all, can still be seen through the waves they produce. It's like suddenly being able to hear in a world you thought was silent. What's even more astonishing is that these waves can reach us from across the entire observable universe. They don't weaken much with distance. If the merger is strong enough, and our detectors are sensitive enough, we can detect black holes from billions of light-years away, back when galaxies were still young and the cosmos was a very different place. It's also possible to use these waves as cosmic rulers. By measuring the signal's shape and strength, we can estimate how far away the event occurred. Combine that with information from traditional telescopes. If we're lucky enough to get light from a companion event, and we can begin to map the universe in an entirely new way. Perhaps most exciting of all is what we don't know. Gravitational waves might reveal objects we've never imagined. black holes of unusual mass, or mergers that challenge our models of star formation. They might help us detect exotic physics, like cosmic strings or phase transitions from the early universe. Every new signal carries the potential for surprise, and all of this began with a ripple, a wave that started in the silence between two spiraling black holes, travelled for over 1 billion years, and gently nudged a mirror on Earth by less than the width of a single atom. Gravitational waves are not just a new kind of observation, they are a new sense, a way of feeling the universe move, a way of knowing that even in the deepest darkness something is happening, something powerful, something real, a drumbeat from the void, a song made of space-time, and once you start listening you realize it's been playing all along. For most of human history, astronomy has been a silent art. We watched the sky and measured its light, visible light, then radio waves, X-rays, gamma rays, but always light. Whether through telescopes or satellites, we explored the universe with our eyes, not our ears. And so, the cosmos seemed like a silent film. Beautiful, but mute. Then, in 2015, the universe made a sound. It wasn't the kind of sound you'd hear with your ears. It wasn't carried by air or thundered through space. It was a ripple, a tiny shiver in space-time itself. A cosmic whisper that passed through Earth unnoticed, except by a pair of machines designed to listen in the quietest way imaginable. This is the story of LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is not one telescope, but two, twin observatories located in Washington and Louisiana, separated by thousands of kilometers, but synchronized like instruments in a duet. Their job is to detect the most subtle change a human being has ever tried to measure, a stretch or squeeze in space smaller than the width of a proton. Each LIGO facility has two long arms, stretching 4 kilometers in an L shape. At the end of each arm is a mirror, and a laser beam is split to travel down both arms at once. When the beams bounce back and reunite, they should be perfectly in sync, unless something has changed. If a gravitational wave passes through, it ever so slightly alters the length of one arm relative to the other. The laser interference pattern shifts, revealing that the space between the mirrors has stretched or compressed. Not the mirrors themselves, space itself. It's a method that requires unbelievable precision. LIGO must detect changes in length as small as 1/10,000th the diameter of a proton. That's like measuring the distance to the nearest star and noticing if it changed by the width of a human hair. The environment must be perfectly still. Vibrations from traffic, waves on the shore, even passing birds can introduce noise. The system is buried in vacuum chambers, isolated from earthquakes, temperature changes, and cosmic rays. Even with all of that, most of what LIGO detects is not from the stars, but from Earth. But every once in a while something different arrives, a ripple that fits no earthly pattern, a shape in the noise that matches predictions made decades ago. And when that happens, the quiet becomes a song. On September 14th, 2015, LIGO was still warming up after a long series of upgrades. Scientists had only just begun the first official observing run of the new system. Then, just before sunrise, a signal appeared. It lasted only a fraction of a second, a low-frequency thump that rose into a brief chirp, like the soft twang of a cosmic cello string. Both detectors registered it almost simultaneously. The signal matched exactly what general relativity had predicted. Two black holes, one about 36 times the mass of the Sun, the other about 29, spiraling together, colliding, and forming a single spinning black hole. The event occurred over 1 billion light-years away, yet the waves it produced still rippled across space, passed through Earth, and gently nudged LIGO's mirrors. This was the first direct detection of gravitational waves. It confirmed Einstein's prediction from a century earlier, but more than that, it gave us a new way of experiencing the universe. For the first time, we could hear space. Scientists took the signal and converted it into sound. The result was a soft chirp, rising in frequency and pitch as the black holes spiraled closer, peaking at the moment of the merger, then vanishing into silence. It's not loud, it's not dramatic, but it's unmistakable. A thud from the dark, the cosmos clearing its throat. Since then, LIGO and its European partner Virgo have detected dozens more mergers. Each one carries a slightly different tone, like different instruments playing the same kind of song. Some are deep and slow, massive black holes merging with thunderous grace. Others are quick and sharp, like distant drum beats. There are binary neutron stars too, which produce longer, more drawn-out signals, sometimes accompanied by a burst of light. Gravitational wave astronomy is often compared to adding a new sense to our toolkit. If electromagnetic telescopes let us see, then LIGO lets us hear. It gives us access to a part of the universe that was previously invisible, events that emit no light at all, taking place in the deepest dark. With gravitational waves, we can now detect black holes that are completely hidden, yet still shape the cosmos around them. The precision is staggering. From a single chirp, scientists can calculate the masses of the merging black holes, their spins, their distance from Earth, and how much energy was radiated away. They can even estimate how fast the final black hole is spinning, and as the catalogue of detections grows, patterns begin to emerge about where these black holes live, how they were born, and what they might tell us about the life cycles of stars and galaxies. What LIGO hears is not just sound, but motion, acceleration, transformation. It's the music of gravity itself. And the discoveries are only just beginning. Plans are already underway to make LIGO more sensitive, to detect more distant events, smaller mergers, or even entirely new phenomena. Future detectors like LISA, a space-based interferometer, will stretch across millions of kilometers and open up a new range of frequencies, listening for slower, more massive dances between supermassive black holes. The universe is not a silent film. It is an orchestra we're just now learning to hear. Every chirp is a chapter, every thud a footnote in the story of space. And each time LIGO hears something new, the cosmos becomes a little less distant, a little more familiar. It's strange to think that we live in a time when this is possible, that from the surface of a small blue planet we can measure the bending of space-time caused by two invisible objects a billion light-years away. But we can, and we are. The universe speaks in ripples, and now, at long last, we're listening. Not all black holes are created equal. Some are born from the collapse of dying stars, a few times the mass of our sun, quiet and unassuming as they drift through the galaxy. But others are giants, monsters really, sitting at the hearts of galaxies, hoarding millions or even billions of solar masses. These are supermassive black holes, and when they merge, the universe pays attention. Every large galaxy we've studied closely appears to have one of these beasts at its centre. The Milky Way has one, a black hole called Sagittarius, a star. With a mass of around 4 million suns, it's not very active right now, just sitting quietly in the galactic core, but it's there, keeping watch over the swirling stars, gas and dust that orbit it like planets around an invisible sun. Supermassive black holes are a mystery in many ways. We don't fully understand how they form. They're too massive to be the result of a single star's collapse. They may grow from smaller black holes, accumulating mass over billions of years. Or perhaps they were seeded in the very early universe, formed directly from dense clouds of primordial gas. However they began, they've become cosmic anchors, stabilizing their galaxies, shaping the growth of stars and regulating the flow of matter. But galaxies don't sit still. Over time, gravity pulls them together, and when two galaxies get close enough, they begin an elaborate and violent interaction. Stars pass near each other, their orbits twisting and reshaping. Clouds of gas collide and compress, triggering waves of new star formation. Spiral arms distort. Tidal tails stretch out like streamers. The galaxies begin to lose their individual shapes and melt into one another. At the center of each galaxy, the supermassive black holes continue to sit. Massive, patient, and entirely unaffected by the chaos outside. But gravity doesn't forget. As the galaxies merge, so do their central black holes, at least eventually. It is not immediate. In fact, the process can take hundreds of millions of years. But little by little, they are drawn together by the very stars and gas that swirl around them. At first, the black holes sink toward the center of the newly forming galaxy. This is driven by dynamical friction, a kind of gravitational drag. As a massive object like a black hole moves through a sea of stars, it disturbs them, leaving a wake of overdensities behind. That wake tugs back on the black hole, robbing it of momentum and slowly dragging it inward. It's as though space itself resists their movement, urging them closer together. Eventually, the two black holes form a binary system. They begin to orbit one another, circling at the heart of a galaxy now reshaped by their presence. Their mutual orbit tightens as they interact with nearby stars and clouds of gas, flinging them outward in complex three-body interactions. Each gravitational kick carries away energy, shrinking the orbit bit by bit. But here's the strange part. This process can stall. It's known as the final parsec problem. At very small separations, about a few light years, the black holes run out of stars to interact with. Without enough material nearby to absorb their orbital energy, their spiral can slow dramatically. For years, scientists debated whether many supermassive black hole binaries might be stuck like this, unable to get close enough for gravitational waves to take over. Recent studies suggest that galaxy cores are messier than we once thought. Gas clouds, stellar asymmetries, and even traxial galactic shapes may help bridge that final gap. And once the separation shrinks below a light year or so, gravitational waves begin to dominate. From that point on, the black holes spiral inward with increasing speed, their masses and motion sending out massive ripples through space-time. Unlike the mergers of stellar black holes, which last fractions of a second, supermassive black hole mergers unfold more slowly, radiating longer, lower-frequency gravitational waves. These are too low in frequency for LIGO to detect, but future observatories like LISA, the Laser Interferometer Space Antenna, will be able to pick them up. LISA will float in space, with detectors separated by millions of kilometers, designed to listen for these deep, slow thuds from across the universe. The energy released in a supermassive merger is staggering. For a brief moment, the output in gravitational waves may exceed the combined luminosity of all the stars in the visible universe. But again, there is no light, no flare, no sound. Just a tremor in the cosmic web, rippling outward for billions of years. These mergers can also have strange after-effects. The resulting black hole, depending on the spins and directions of the merging pair, can receive a gravitational recoil, a sort of cosmic kick. If the kick is strong enough, it could send the black hole hurtling through space at thousands of kilometers per second. In extreme cases, the new black hole might even be ejected from its galaxy entirely, doomed to wander the void between galaxies forever. That's not just theory. Astronomers have found possible signs of displaced black holes, galactic centers that seem to be missing their expected anchor, or active black holes located far from their usual home. These rogue giants may be the products of such recoils, flung away by the immense physics of their own creation. Supermassive black hole mergers are not just events, they are transformations on a galactic scale. They shape galaxies, redirect matter, and define the evolution of the universe itself. When two such giants come together, they don't just change each other, they change everything around them. And perhaps most remarkable of all is that these enormous violent mergers, spanning millions of years and involving masses beyond imagination, are completely invisible to the eye. There's no blaze, no explosion, no swirling jet of plasma. Only gravity, only space-time shifting and bending, letting us know that something enormous has happened. One day, perhaps sooner than we expect, our instruments will be sensitive enough to listen in on one of these cosmic unions as it happens. We may hear the slow song of a galaxy's heart becoming whole again. And when we do, it will be another reminder that in the vast darkness of space, even the quietest events can leave the deepest marks. When two black holes merge, they don't simply vanish or explode. They become one, bigger, heavier, and almost always spinning. But the moment of merger isn't the end of the story. In fact, what happens just after is one of the most fascinating parts of the whole process. It's the cosmic version of the quiet after a storm, except in this case, the silence is absolute and the stillness is earned. The final black hole formed from the union of the two original ones carries with it all the mass that wasn't flung away as gravitational radiation. In many cases, that's almost all of it. But some mass is indeed lost, not as matter, not as light, but as pure gravitational energy. It's a remarkable trade. Mass becomes wave, and that wave travels across the universe as a gentle stretching and squeezing of space-time. But the new black hole isn't immediately serene. It's distorted, shaken by the violence of its own birth. It vibrates, not with sound, but with the geometry of space itself. These vibrations are called ring-downs, and they're the final phase of the gravitational wave signal. Think of it like a bell that's just been struck. A few sharp tones followed by a fading resonance. These ring-downs are more than just a mathematical curiosity. They hold precise information about the black hole's properties, its final mass, its spin rate, and even hints about whether general relativity holds true under extreme conditions. If anything were different, if gravity behaved in some new or exotic way, it would show up in the fading echoes of this ring-down phase. So far, Einstein's predictions have passed every test. But there's another layer to this story, one that sounds almost whimsical. The cosmic recoil. When two black holes merge, the energy and momentum they radiate isn't always distributed evenly. If one black hole was more massive or spinning in a different direction, or if their orbits were slightly off-center, the gravitational waves they emit will be asymmetrical. And just like a cannon recoils when it fires, the final black hole gets a kick. This kick is called a gravitational recoil or a black hole kick, and in some cases it can be powerful enough to launch the black hole through space at thousands of kilometers per second. The numbers can be astonishing. Kicks of several thousand kilometers per second are possible in theory, and a few have been observed at high enough speeds to raise eyebrows. Most of the time, these kicks don't do anything dramatic. The black hole just shifts position, drifting slightly off-center within its host galaxy or star cluster. But in extreme cases, if the kick is strong enough and the environment is light enough, the black hole can actually escape its galaxy entirely. It becomes a rogue, adrift in intergalactic space, carrying with it no stars, no planets, just the memory of the collision that set it free. These runaway black holes are difficult to find, but not impossible. Some may be detected by the effects they have on surrounding gas. If they plough through a cloud, they might leave a trail of heated material. Others might be spotted indirectly by looking for active galactic centers that seem suspiciously empty, like a city missing its skyline. Meanwhile, the black hole itself is settling down. The ring-downs fade, the distortions smooth out. It becomes spherical, or nearly so, with the smoothest possible surface allowed by physics. It still spins, most merged black holes do, but the wobble is gone. What remains is a silent, spinning void, its past encoded only in mass, spin, and perhaps a subtle change in location. This quiet state is what physicists call a Kerr black hole, a stable configuration that's fully described by just a few properties. It has no hair, no scars, no record of how it came to be. Two black holes may have danced and collided, but the final product is indistinguishable from any other black hole with the same mass and spin. It's one of the strangest features of black hole physics. The idea that all the complexity of the merger gets erased at the horizon. The waves go out, but the story ends at a smooth edge. But those waves are crucial. They're the reason we know any of this has happened. From the shape of the ring down, scientists can tell how much mass was radiated away. They can measure the final spin, and perhaps most importantly, they can check if the waveform matches predictions from general relativity. So far it does, with almost eerie precision. Over time, the final black hole becomes just another gravitational anchor, shaping the orbits of stars or gas clouds, drifting through its galactic home, or perhaps spinning silently in the emptiness between galaxies. Unless something disturbs it, another merger, a passing star, it will remain exactly as it is, unchanged for billions of years. In the vast slow rhythm of the universe, these post-merger moments are brief. The merger itself may have taken millions or billions of years to set up, and the ring down may last just seconds. But in those seconds, something remarkable happens. Two completely separate regions of warped space and time become one. Two event horizons merge, their surfaces fusing into a single horizon. A process that is, in every sense, irreversible. There's no light show, no fire, no debris. The aftermath of a black hole merger is defined by what's missing. Missing energy, missing individuality, missing escape. But also by what's gained. A new black hole, more massive, more stable, more complete. What's left behind is not just an object. It's a gravitational statement, a calm in the cosmic sea. The final wave has passed, the ripples are fading, and space is once again still. But stillness doesn't mean emptiness. The merged black hole now sits as a monument to forces beyond comprehension. A monument that doesn't glow or speak, but which warps everything around it, subtly yet profoundly. A scar in space-time, healed but never forgotten. And somewhere, travelling outward at the speed of light, are the last whispers of that union. The ring-down's final sigh, a gravitational echo still rippling through the fabric of the universe long after the event has ended. Time is a curious thing, even under normal circumstances. It flows in one direction, gently, invisibly. Like a stream we all drift along without ever quite knowing how or why. But near a black hole, time becomes more than a quiet current. It stretches, bends and slows in ways that defy ordinary experience. It becomes a landscape with hills and valleys, where the speed of a clock depends on where it's ticking. As two black holes spiral toward one another, they aren't just warping space, they're also twisting time. The closer you get to their event horizons, the slower time moves, at least from the perspective of someone watching from far away. This isn't metaphor. It's a measurable effect, predicted by general relativity and confirmed by experiment again and again. Let's imagine for a moment that you had a clock orbiting just outside a pair of merging black holes. It's perfectly accurate, perfectly stable. But as it moves closer to the warping mass, each second it counts appears to take longer when viewed from a distant location. If you were far away, floating comfortably in interstellar space, watching that clock through a powerful telescope, you'd see its hands move more and more slowly. The ticks would stretch out. A minute would take longer than a minute. An hour could take a day. And as that clock approaches the event horizon, its ticks would begin to freeze. From your faraway viewpoint, the merger seems to slow, as if pausing at the very edge of reality. The black holes draw closer and closer, but never quite touch. Instead, they hover in place, frozen in a moment that never ends. This illusion is the result of extreme gravitational time dilation. The gravitational field near the merging black holes is so intense that it bends time itself. From the point of view of someone riding along with the black holes, if such a thing were possible, the merger would happen swiftly. The event horizon would be crossed, the two black holes would combine, and the final ring-down would play out in real time. But for us, watching from a safe distance, the story is different. The merger appears to unfold in slow motion. The black holes seem suspended in their final moments, as if space-time itself is reluctant to let them go. And in a sense, it never does. For a faraway observer, the last light emitted just before the horizon is crossed becomes increasingly redshifted, stretched into invisibility. The final flash of information fades until it is lost, not because it vanishes, but because it takes forever to arrive. This raises a strange possibility that from our perspective the moment of merger is never truly over. The collision, so dramatic and final from within, becomes an eternal event from without. A pause button pressed by the curvature of space-time itself. It's a bit like watching a star fall into a black hole. As the star nears the horizon, its image slows and dims, fading to black as time stretches out. The star never seems to fall in, even though we know it must. Its descent becomes a ghost of motion, lingering at the edge of perception. The same is true for merging black holes. Their final embrace, so full of energy and gravitational drama, becomes a kind of gravitational echo that never quite fades. The merger creates ripples that travel across the cosmos, gravitational waves that reach us, carrying the rhythm of that union. But the image of the black holes themselves, if we could see it, would remain frozen in that last moment, hanging on the edge of time. It's tempting to think of time as universal, as something that ticks the same for everyone, everywhere. But it isn't. Time is local, personal. It ticks faster or slower depending on where you are and how fast you're moving. Near a black hole, those differences become enormous. A twin who ventured too close might return younger, while centuries had passed for everyone else. In the case of a merger, the distortion is even more dramatic. The warping of space-time near the event horizons is so extreme that for an outside observer, everything grinds almost to a halt. Even the merger itself, that swirling, spiraling dance of titanic forces, becomes a kind of frozen ballet, a shape rather than a sequence, a sculpture in time. This idea, that events can be finished in one frame but eternal in another, is one of the more poetic consequences of relativity. It suggests that the universe is full of unfinished moments, playing out at different speeds depending on where you stand. For the black holes, the merger is over. They've become one. The gravitational waves have been sent. The final black hole has rung like a bell and gone still. But from far away, that last orbit may still be unfolding, slowly, delicately, almost imperceptibly. Some physicists describe this as a kind of holographic surface. The information of everything that has fallen in remains, stretched out across the event horizon like a memory in space-time. It isn't gone. It's just unreachable, slowed beyond access. Whether that information is preserved or lost forever is one of the great mysteries of physics. But the stretching of time itself is not a mystery. It's a feature of the universe we live in. Even our instruments, so finely tuned to catch gravitational waves, experience this effect in their own way. What they detect, the chirp, the ring down, is not a frozen image, but the energy that escaped before the final fusion. The waves we measure are not the black holes themselves, but their last loud breath, sent before time closed in around them. So when we say the black holes have merged, we speak from the frame of those waves. We speak from the energy that arrived, the signal that reached our detectors. But in another frame, farther out in the galaxy or across the universe, that merger may still be unwinding, still slowing, still frozen. And perhaps in some deep and dreamlike sense, the universe holds that moment in place, not because it must, but because gravity allows it. Because time, near the edge of a black hole, becomes something less like a river and more like a painting. A moment, caught forever on the canvas of space-time, quiet, still, suspended in the dark. Imagine drifting through the silence of deep space, no stars nearby, no sunlight, just the hush of eternity and the distant invisible pull of something immense. Ahead of you, two black holes, not dots, not holes, not even darkness really, just curves in space, invisible shapes where light itself has lost its way. They orbit each other like twin dancers locked in a final waltz, moving with a grace that belies the violence of their union, and you're falling toward them, You don't feel it at first. There's no wind in space, no sound, just a subtle sense that the stars are stretching, the constellations bending ever so slightly as you begin to descend through the warped geometry of space-time. There's no up or down, directions lose meaning, everything is being pulled inward, curved gently toward inevitability. As you fall closer, time begins to play tricks. Your heartbeat still thumps steadily in your chest, but around you, everything else begins to slow. The black holes, spinning and circling, seem to drift more languidly. Their motion, so intense just moments before, becomes syrupy and surreal. From your perspective, you're moving faster and faster, but from far away, someone watching you would see the opposite. Your descent would appear to slow, stretched across an infinite moment, as if the universe itself can't bear to watch. And then the stretching begins, not metaphorically, but physically. You've heard the term before, spaghettification. It sounds cartoonish, but in the presence of a black hole, it's very real. Gravity is stronger at your feet than at your head. The difference in pull becomes extreme. Your body, so used to being held together gently by the Earth's gravity, begins to feel the strain of tidal forces. These are not waves, but differences in gravity across your form. If you were made of something rigid, you might resist, but you're not. You're soft, delicate, organic. The experience isn't painful, at least not at first. It's just strange. You feel as if you're being drawn out like a thread, your senses beginning to blur. Vision becomes distorted. The idea of a single perspective starts to fray. The black holes grow, not in size, but in influence. Their gravitational fields are no longer distant distortions. They are the shape of your world now. Between the two black holes, space-time churns. If you're unlucky, or very lucky, you fall into the region where their horizons are just beginning to touch. You cross not one threshold, but two. Their event horizons, previously separate, are now tangled together in a final embrace. This space is undefined, not because we lack imagination, but because physics itself stumbles here. Equations break down, coordinates fail. Inside time and space trade places, the direction you once called forward now leads inward, toward the singularity, toward the point where density becomes infinite and the known rules of nature no longer apply. You might expect to see stars or swirling gas like in the dramatic animations, but you don't. Inside the merging black holes there is no light, there is no image, there is no view. You're not watching the universe anymore. You're inside a boundary from which no information can return. And yet, strangely, you still feel, you still think. For a brief moment, awareness lingers like breath on a mirror. In that moment, the merger peaks. The horizons stretch and pull, wobbling from the violence of their own collision. The ring-down begins, the new black hole, newly formed, begins to settle, to hum, to lose its imperfections. Outside, gravitational waves ripple away, but inside, you wouldn't know. The waves are gone before they reach you, their energy spent in the void beyond your prison. And still, time slips. Your thoughts begin to drift apart like leaves on a slow-moving stream. The concept of before and after starts to smear. Maybe you recall a sound, a memory, a flicker of sunlight on a calm morning. Maybe you forget what morning means. If consciousness survives the fall, and that is a very big if, then it must be experiencing something unmoored from all familiar structure. There is no clock here, no calendar, no language for what this is. Just a moment, stretching forever. Back in the realm of equations, physicists debate whether you would be torn apart before you even reach the center. In smaller black holes, the tidal forces are so intense that they would shred you long before you neared the singularity. But in larger ones, like the supermassive titans at galactic centers, the fall might be gentler. You could cross the event horizon without even noticing, until it was far, far too late. But a merger complicates things. The space-time around two black holes in collision is wild and unstable. There are no tidy paths, no smooth descent, just a roiling storm of geometry folding in on itself. Your journey through that space would not be straight or calm. It would be a fall through a twisting canyon of gravity, with no solid floor at the bottom. And then, eventually silence. Not just the absence of sound, but the absence of direction, of definition, of self. Some theories suggest that, at the singularity, all matter compresses into an infinitely small point. Others suggest new universes might bud off inside these regions. We do not know. The laws of physics as we understand them go dark at that depth. The equations run into infinities. The story stops. But even that end is seen only from your perspective. Outside, the merger has finished. The gravitational waves have travelled billions of light years to reach detectors on a quiet little planet orbiting a yellow star. The signal lasts just a few tenths of a second, a chirp, a blurp, and it's over. Your fall, meanwhile, continues. To fall into a black hole is to fall forever. To fall into two merging black holes is to be caught in a transformation so absolute that even time cannot hold on. It's not an explosion, it's not a crash, it's more like a hush, a deep, cosmic exhale, a vanishing act performed in silence and shadow. And perhaps, as your last coherent thought begins to dissolve, you realize this: you are not destroyed. You are translated, converted into geometry, stretched into the curvature of space itself. You've become part of the merger, a line in its silent equation, a moment in the infinite. The universe goes on. The stars keep burning, but a part of you now lies folded into the fabric of space-time, cradled in the arms of gravity's strangest embrace. Black holes are invisible. That's not a poetic exaggeration. They genuinely cannot be seen. They emit no light, reflect nothing, and hide everything that falls within their boundaries. They are the ultimate cosmic secret keepers, and yet somehow we know what they look like. We've watched them spiral, crash, stretch light around them like glass marbles, and settle into serene spherical silence. Not with our eyes, but with our models. Since we can't see black holes directly, we simulate them. And to do that well, we need something a little more powerful than your average laptop. Across the world, supercomputers are humming. Vast, warehouse-sized brains that crunch numbers faster than you can blink. These machines take in Einstein's equations, factor in the chaos of space-time, and spit out something astonishing, a visual glimpse into the invisible. Let's start with a well-known example. The simulations from NASA that depict binary black hole mergers. You may have seen them. Two glowing disks of warped light circling each other, their forms distorted and stretched by gravity itself. These aren't science fiction renderings. They are quite literally mathematics made visible. Each frame in those simulations represents thousands of calculations: mass, spin, orbital dynamics, relativistic beaming, time dilation, all woven together into a fluid moving picture. The light swirling around the black holes is not from the black holes themselves, but from the gas and dust that orbit them, bending and stretching as it tries to flee. Some of that light makes it out, most does not. But here's where it gets stranger. In a black hole simulation, you have to account not just for how things move, but for how they appear. In extreme gravitational environments, light doesn't travel in straight lines. It curves. It loops. It sometimes circles a black hole several times before heading out toward the viewer. That means what you see is not always where things are. You might be looking at the far side of a black hole, because light from behind it can be bent all the way around to the front. These optical illusions aren't bugs, they're features, and they're baked into the code of our most advanced models. When you watch one of those swirling simulations, you're not watching a guess. You're watching physics faithfully rendered. But there's more. Consider the Event Horizon Telescope, the international collaboration that produced the first real image of a black hole's shadow in the galaxy, M87. The image itself is blurry and soft, a glowing donut of orange light with a dark center. But behind that image lies a mountain of simulation work. To interpret the data, scientists had to simulate what a black hole should look like from every possible angle, with every possible spin rate, surrounded by every reasonable configuration of light-emitting matter. They created libraries of black hole appearances, thousands of virtual universes for comparison. Only by matching these simulations to the actual data could they be sure they were seeing what they thought they were seeing. In a way, the image wasn't captured, it was confirmed. That's the strange poetry of simulating black holes. You don't see them directly. You simulate what you expect to see, based on the laws of physics, and then test whether the universe agrees. These simulations aren't just pretty animations, they're tools. With them, scientists can test theories about how black holes behave, how they merge, how they spin, how they might devour nearby stars or fling matter into space at nearly the speed of light. By tweaking the input, changing the mass, the distance, the initial spin, you can watch entirely new black hole systems play out in virtual space-time, and sometimes they reveal surprises. In early simulations, physicists discovered that the collision of spinning black holes could create massive kicks, sending the final merged object flying through space. Others showed how gravitational waves from mergers carry away vast amounts of energy, reshaping the orbits of nearby stars. Still others revealed complex behavior near the event horizon, swirling patterns of light and motion that no one had expected. Even more recently, simulations have started to incorporate not just black holes, but their environments. Gas, dust, magnetic fields, even other stars. These zoomed-out simulations help us understand not just what black holes do, but how their presence shapes galaxies. In fact, some simulations go further still. They don't just model one or two black holes, but entire galaxies full of them. Using high-powered cosmological simulations, scientists can watch as galaxies collide, form binary black holes, and eventually merge. These programs track billions of particles across billions of years, compressing the history of the universe into something we can actually see. There's something beautiful about this process. You start with equations on a page, cold, elegant, untouchable. You feed them into a machine. The machine thinks, calculates, loops through possibilities, and out comes something visual, something tangible, a swirling ballet of matter and light that captures a moment no eye could ever witness. In this way, scientists become a kind of cosmic cinematographer, not creating fiction, but revealing fact. They turn the unseeable into spectacle, not to dazzle, but to understand. And yet, the artistry is hard to ignore. A good black hole simulation is a kind of science art. The shapes, the symmetry, the flowing motion of gravity, it stirs something, awe, maybe, or humility, or simply a quiet curiosity that lingers long after the final frame. Because when we watch these simulations, we're not just seeing what is, we're seeing what could be, what has been, what is happening right now, in some distant corner of the cosmos where two black holes are beginning their spiral dance. Somewhere out there, a merger is unfolding. We'll never see it with our eyes, but with code and curiosity and a few million processor cores, we can imagine it. We can render the unseeable, and in doing so, we bring a little bit of that hidden universe home. In the stories we tell, black holes are usually cast as villains, devourers of stars, destroyers of worlds, engines of annihilation. They're the monsters lurking at the center of galaxies, pulling in anything that dares to get too close. But like many characters in the cosmos, black holes are more complex than they seem. For all their appetite and mystery, they also serve a deeper purpose. In fact, it may not be an exaggeration to say that the universe needs black holes. Yes, they swallow light. Yes, they stretch time, but they also shape galaxies, regulate the birth of stars, and stir the cosmos in ways that are not just necessary, but creative. Start with the centers of galaxies. Nearly every large galaxy we've observed, including our own Milky Way, contains a supermassive black hole at its core. These aren't ordinary black holes, they're titans, millions or even billions of times the mass of our Sun, condensed into a region smaller than the solar system. You might think of them as quiet anchors, but they're anything but quiet. When a supermassive black hole is feeding, when gas, dust or stars stray too close, it can light up with astonishing power. The infalling material forms an accretion disk, a swirling platter of matter spiraling inward. As it does, friction and magnetic fields heat the gas to extreme temperatures, releasing torrents of radiation. These glowing beacons are called quasars, and they can outshine the entire galaxy that hosts them. But the spectacle isn't just for show. That energy affects everything around it. The radiation from an active black hole can heat and blow away nearby gas, halting star formation in its tracks. It's like a thermostat for the galaxy. When things get too hot and crowded, the black hole kicks into gear, pushing material away until things cool down again. This feedback loop is part of what keeps galaxies from growing uncontrollably. Without it, some galaxies might form too many stars, too fast, using up their gas in a cosmic blaze of unsustainable growth. Instead, black holes help keep the process balanced. They don't just end things, they guide them, and their influence extends far beyond their reach. The jets from active black holes, narrow beams of charged particles launched at nearly the speed of light, can stretch across hundreds of thousands of light years. These jets slice through galaxies and beyond, punching through the cosmic medium, stirring it, energizing it, and redistributing material that might otherwise stay stuck. It's cosmic landscaping on the grandest scale. In galaxy clusters, those sprawling families of galaxies bound by gravity, black holes play a particularly important role. Many clusters contain huge reservoirs of hot gas, rich in the elements needed to form new stars. Left alone, this gas should cool and condense into galaxies full of bright new stars. But strangely, it doesn't. The gas stays hot and diffuse. The reason? Black holes. Specifically, the ones at the centers of the largest galaxies in the cluster. As they feed, they release energy, not just in radiation, but in sound waves, jets, and bubbles of high-energy plasma. These outputs stir the gas, preventing it from cooling too quickly. The result is a slow simmer, not a runaway blaze. Star formation becomes a measured, gentle process, one guided by a quiet gravitational engine. Even at the small scale black holes contribute. When massive stars collapse into black holes, they often do so in violent supernovae. These explosions scatter heavy elements, carbon, oxygen, iron, into space. Those elements eventually become part of new stars, planets, and even life. In a very real way, we owe our existence to the deaths that lead to black holes. They are part of the life cycle of the universe, not separate from it. And while we're on the subject of life, consider this. Without black holes, galaxies might be too chaotic or too quiet, too many stars or not enough, too much gas or too little. The delicate balance that makes planetary systems stable and habitable might not arise at all. Our own galaxy has been shaped by its central black hole for billions of years. Its quiet influence has helped steer the Milky Way's evolution, creating the kind of structured, spiraled galaxy where stars like our Sun can live calm, long lives. There's even a theory, still speculative, but tantalizing, that the earliest black holes helped kickstart the formation of galaxies themselves. In the early universe, tiny black holes may have acted as gravitational seeds, drawing in gas and dust to form the first galactic structures. Without them, the universe might have remained a featureless fog for far longer. In that sense, black holes didn't just emerge from the cosmos, they helped shape it, so while their reputation as destroyers is not unearned, it's incomplete. Black holes are sculptors, balancers, recyclers. They take in chaos and release order. They feed on matter and give back momentum. They are not just the end of stars, they are the quiet custodians of everything that follows. Perhaps that's the most surprising thing of all. In the heart of nothingness, the universe finds a way to keep going. Black holes may seem like cosmic full stops, but they're more like commas, pauses in a longer sentence, moments of change in an ongoing story. And in that story, darkness does not always mean an end. Sometimes it's where everything begins again. Wind the universe back, past the stars, past the galaxies, past the swirling nebulae and brilliant quasars. Keep going, beyond the familiar constellations and clusters, until everything becomes compressed, hot, and new. The cosmic clock resets, and we arrive at the early universe, a time before galaxies had names, before black holes were infamous, before the sky was dotted with light. This is where the story of black holes across time truly begins. In those first few 100 million years after the Big Bang, the universe was a thick fog of energy and particles, still cooling from its explosive beginning. Gravity was already at work, gently tugging together tiny fluctuations in the fabric of this new cosmos. And it was in those dense, chaotic regions that the seeds of black holes may have first formed, not as the aftermath of stars, but as relics of the universe's birth itself. These hypothetical entities are known as primordial black holes. Unlike their stellar cousins, which are born from the death of massive stars, primordial black holes may have formed directly from dense patches of energy in the very early universe. Tiny ones, possibly no bigger than a mountain, or colossal ones, hundreds of thousands of times the mass of the Sun. Some might have evaporated quickly through Hawking radiation. Others could still be lurking, dark and ancient, having survived the universe's long history in silence. Though we've never observed a primordial black hole directly, scientists have searched for them, for the strange bending of the light they might cause, for the subtle signatures of their gravitational influence. If they do exist, they might even account for some of the mysterious dark matter that fills the cosmos. It's a cosmic detective story still unfolding. But black holes, whether primordial or stellar, didn't stay isolated for long. As the universe aged just a little, reaching a few 100 million years old, the first stars ignited. These were the giants, huge, hot, short-lived stars made mostly of hydrogen and helium. They lived fast and died young, collapsing into black holes far more massive than those formed today. These early black holes didn't sit still. They gathered gas, collided with others, and grew quickly, some eventually becoming the monstrous supermassive black holes we now find at the centers of galaxies. In fact, one of the enduring puzzles in astronomy is just how these giants grew so quickly. We've found quasars, blazing black hole-powered beacons, shining from less than 1 billion years after the Big Bang. That's incredibly early. It suggests that black hole mergers and rapid feeding were not rare events in the young universe, but frequent, energetic, and profoundly influential. Back then, everything was closer together. Galaxies were smaller and more chaotic, swirling through space like dancers with no choreography. Collisions were common. 2 galaxies would pass close, their stars rarely colliding, but their central black holes drawn inexorably together by gravity. In time, those black holes would spiral inward, merging in a brilliant invisible flash of gravitational waves. This frenzy of merging didn't just create bigger black holes, it helped shape the cosmic web itself, the vast filamentary structure of the universe, the distribution of galaxies we see today, stretching in threads across billions of light years, was partly sculpted by gravity's persistent effort to bring things together. And black holes played their role as cosmic architects, tugging, merging, radiating energy into their surroundings. As the universe aged, this drama slowed down. Galaxies grew larger and more stable. The space between them expanded. Mergers became less frequent, though they never stopped entirely. Even today, the dance continues, slower, quieter, but still unfolding across the stars. Meanwhile, the black holes born in the early universe have aged into elders. Some remain quiet, barely feeding, content to sit at the centers of mature galaxies. Others still blaze as quasars or power radio galaxies with enormous jets. Many have merged more than once, growing heavier and more complex with each collision. They carry a history written not in words, but in mass and spin, a gravitational diary billions of years in the making, and they are still teaching us about time itself. The black holes we observe now often bring us echoes from the past. When we detect gravitational waves from a merger, those waves have travelled across the expanding universe, sometimes for billions of years, before reaching Earth. Each ripple is a message from long ago preserved by the cosmos with exquisite precision. These events help us build a timeline, not just of black holes, but of everything. They allow us to test theories about the early universe, the growth of structure, the formation of galaxies. Every wave is a data point, a story, a clue. In a strange twist, black holes, once seen as the endpoints of matter, are now some of the best tools we have for studying beginnings. They tell us how stars lived and died. They reveal how galaxies grew. They whisper about the conditions of the infant universe and hint at the strange physics that may have reigned before atoms had even formed. Time may seem to vanish inside a black hole, but across the cosmos, black holes help mark time's passing. Each merger, each burst of radiation, each flicker from a distant quasar is a tick of the cosmic clock. And that clock, it seems, has always had black holes near its centre. As we look further and further out into space, we're also looking further back in time. And almost everywhere we look, black holes are there. Quiet, powerful, mysterious companions to the universe's unfolding story. From the first moments after the Big Bang to the swirling galaxies of today, they have shaped what we see, sculpted what we don't, and helped turn chaos into structure. They are not just remnants, they are reminders of how far we've come and of the immense hidden forces still at work behind the stars. Gravity doesn't shout, it doesn't spark or sizzle, it doesn't glow or crackle like electricity, or bind atoms together like the strong nuclear force. In fact, among the four fundamental forces of nature, gravity is the weakest by far. A small magnet can lift a paperclip against the gravitational pull of an entire planet. That's how feeble it is. And yet gravity rules everything, not with brute force, but with reach, with elegance, with infinite patience. Black holes are some of gravity's most dramatic achievements, and their mergers are among the most powerful events in the universe. But behind all that spectacle is a soft, relentless pull that begins long before the fireworks. Gravity doesn't rush. It doesn't need to. It simply waits and wins. It's easy to forget how extraordinary that is. On the smallest scales, gravity is barely noticeable. You don't feel the gravitational pull of your coffee cup or your phone, even though technically it's there. But as objects get bigger, planets, stars, galaxies, the effects start to build, and there's no upper limit. Gravity adds up, it accumulates, it gets stronger with mass, and it never turns off. There's no such thing as anti-gravity in the way there's antimatter or repelling magnets. Gravity only knows how to attract. That one direction, always inward, always pulling, gives gravity a kind of poetic simplicity, a quiet determination. It's what shapes moons into spheres, holds planets in orbit, sculpts galaxies into spirals. It's the reason stars burn, the reason time bends, the reason tides move. Even your body is pulled slightly by the moon and the sun every day, though you may never notice. And then, on the grandest scale, gravity writes the structure of the universe itself. Imagine space as a vast dark canvas stretched across billions of light years. Now imagine drops of invisible ink splattered across that canvas, little pockets of matter that slowly draw more and more in. That's gravity's doing. Over time it takes randomness and turns it into shape. It spins clouds of gas into stars. It binds those stars into galaxies. It weaves those galaxies into clusters, then threads those clusters into the great cosmic web. It doesn't use tools or machinery, just the soft insistence of mass pulling on mass. Even light isn't immune. Though it has no mass, light still follows the curves and folds that gravity makes in space-time. That's why we see gravitational lensing, where galaxies bend the light from other galaxies, creating arcs and halos and mirages. It's a visible echo of an invisible force, and nowhere is that force more mesmerizing than in a black hole merger. Two black holes born from long-dead stars can drift through space for billions of years before their paths cross. When they do, gravity takes over, subtle at first, then slowly stronger. They begin to orbit, not in circles but in tight spirals that bring them ever closer together. They lose energy not through fire or friction, but through the rippling of space-time itself. Gravity gives up just a little of its structure, just enough to draw them in. That spiraling dance, that long courtship of collapse is all gravity. No flames, no collisions of atoms, just mass, motion, and curved geometry. And at the end, when the two black holes finally collide, the power released isn't from nuclear fusion or chemical reaction, it's from gravity letting go. The final coalescence, the ring down, the release of gravitational waves, it all comes from the quiet power of curves straightening themselves out. The universe doesn't need an explosion to make a statement. Sometimes, a tiny shift in space-time is louder than a billion suns, and it doesn't end there. Gravity continues its work long after the merger is done. The new black hole settles into place, spinning, warping space around it like a whirlpool in the ocean of reality. It may drift through its galaxy, or it may sit quietly in the center. It may pull in new matter, or remain still for eons. But always, it waits. It listens. It pulls. This kind of dominance isn't flashy. Gravity doesn't need a stage. It's in the background of every moment, every motion, every shape. And perhaps that's why it feels so trustworthy. Unlike the strong nuclear force, which only works in the heart of atoms, or the weak force, which governs radioactive decay, or electromagnetism, which flickers on and off, gravity is everywhere, all the time. It holds your feet to the floor, it keeps the Earth spinning around the sun, it keeps the sun bound to the galaxy, and it keeps the galaxy tugging gently on every other galaxy, creating the vast, invisible tension that shapes everything we can see. It even affects time. In strong gravitational fields, clocks tick slower. This isn't science fiction. It's been measured with satellites and atomic clocks. Stand on a mountain, and time moves ever so slightly faster for you than it does at sea level. Get too close to a black hole and time practically freezes. Gravity doesn't just pull on space, it tugs at time itself. In the end, black hole mergers are just one expression of this silent power. A dramatic one, yes, but not unique. Every orbit, every fall, every swing of a pendulum is gravity in motion. The difference is scale. Black holes are the punctuation marks in gravity's grand sentence, the exclamation points perhaps. But the rest of the sentence is still there. The moons, the planets, the comets, the quiet arcs of galaxies spinning slowly in the dark. And while other forces rage, flicker, or vanish, gravity remains. Patient, gentle, inescapable. It doesn't push or prod, it doesn't demand attention, but in the end, it always gets its way. Not through strength, through stillness, through presence, through time, and in a universe full of noise and motion, perhaps that is the greatest power of all. The universe is expanding. That much we know. Every distant galaxy is drifting farther from us, not because we're the center of everything, but because space itself is stretching. The farther something is, the faster it moves away, carried by this quiet, relentless expansion. It's a gentle ballooning, not an explosion. A swelling of the cosmos, slow and smooth. But what if this expansion doesn't last forever? What if, in some deep cosmic future, things reverse? There's a possibility, still theoretical, still mysterious, that the universe might one day stop growing and begin to contract. That space itself might pull inward. Galaxies would draw closer, then collide. Stars would crowd the sky once more, and eventually everything might collapse into a final convergence. The Big Crunch. A cosmic implosion. A mirror to the Big Bang. It's not the most popular theory at the moment. Current observations suggest that the universe's expansion is accelerating, driven by something we call dark energy. But we don't know what dark energy is, or how long it will last. It could fade, it could change, it could turn on us. If it did, gravity might one day reassert its quiet power, and the great unravelling could become a grand reunion. If that were to happen, we'd enter a strange era of convergence. Galaxies, stars, planets, everything would fall inward. Heat would rise, structures would collapse, and black holes, those quiet titans scattered across the cosmic landscape, would begin to dominate. Because black holes don't let go. In this hypothetical future, black holes could begin merging at a faster rate. Galactic centers would collide, stellar remnants would fall into larger holes, smaller black holes might spiral into their bigger cousins, and as this process continues, fewer and fewer black holes would remain, but each one would be heavier, darker, more massive. It would be a kind of cosmic consolidation, a slow gathering of the universe's forgotten fragments. Could it all end with just one final universe-sized black hole? It's a poetic idea, that the universe, which once burst forth from a single, dense, radiant point, might someday return to a similar state, not as bright bang, but as a silent collapse, not as light, but as gravity, the ultimate merger, the final horizon. We don't know if this will happen, but it's a question that touches the edges of both science and imagination. It raises another possibility too. If everything ends up in a black hole, what happens then? Could the fabric of space and time itself buckle under the weight? Could the universe reach a point so dense, so curved, that it becomes something new, another beginning? Some theories suggest a bounce, a universe that crunches and then bangs again, endlessly cycling between birth and collapse. Others suggest an ending more final, a singularity so absolute that nothing escapes, not even time. But maybe the universe won't crunch, maybe it won't bounce, maybe instead black holes will simply take over, not by swallowing everything at once, but by outlasting it. Stars will die, planets will freeze, even atoms might eventually decay. But black holes, especially the big ones, could linger for unimaginable stretches of time, outliving everything else. There's a term for this distant era, the black hole era. It's part of the projected heat death of the universe, where almost all matter has either decayed or fallen into black holes. There will be no more stars, no more light, just scattered black holes drifting in a cold, expanding void. Even then, they won't last forever. According to Stephen Hawking's theory, black holes can evaporate through a slow quantum process, Hawking radiation. Over trillions of years, they would slowly leak energy back into the universe until finally the last black hole winks out. A soft, quiet end. Or is it, if everything merges, if everything evaporates, if even time stretches out to infinity, what's left? Nothing? Or something we just don't have the tools to understand yet? It's tempting to imagine the universe as a living thing, with a birth, a life, a death, with rhythms and cycles like breath. Maybe the Big Bang wasn't the first. Maybe the current expansion is just one phase in an eternal dance. Maybe black holes are not tombstones, but seeds. In some speculative theories of quantum gravity, black holes might give rise to new universes. The singularity at the center of a black hole could be a doorway, not into destruction, but into birth. The end of one space-time could bloom into the beginning of another, each black hole a portal, each merger a reshuffling of the cosmic deck. Again, we don't know. The truth might be more mundane or more strange than we can imagine. But the beauty of science is that it allows room for both questions and awe. Even without answers, even with uncertainty, we can wonder, we can explore, we can dream. Because speculation, when done with care, is a kind of science in waiting, a way of reaching out to what we don't yet understand and asking softly, what if? Could the universe merge with itself? Perhaps not in the literal sense, but in a poetic sense, in a gravitational sense, it already has. Every collision, every collapse, every black hole is a small piece of the cosmos coming back together. And maybe, in the end, gravity's quiet pull will win once again. Not with a bang, not with a blaze, but with a slow, dark, perfect stillness. When we picture black hole mergers, we often imagine a clean, elegant process. Two massive objects spiraling inward over millions or billions of years, slowly shedding gravitational energy until they collide and become one. A cosmic waltz, graceful and inevitable. But space is rarely that tidy. Mergers don't always go as planned. Sometimes they don't go at all. Sometimes the dance is interrupted. The timing is off. A third partner arrives unexpectedly. Or the two dancers fling each other apart instead of joining in union. Even in the quiet realm of black holes there is chaos. Let's start with a twist. Triple systems. Occasionally, three black holes find themselves bound together by gravity, often the result of galaxies colliding, and their central black holes becoming entangled. But three is a crowd in celestial mechanics. These systems are notoriously unstable. Instead of settling into a neat orbit, the black holes jostle, loop, and tug at one another. It's a gravitational soap opera. Over time, one member of the trio often gets ejected, a dramatic cosmic breakup. The remaining pair might eventually settle into a merger-friendly orbit, but the third black hole is flung into space, exiled from the system entirely. These rogue black holes could be drifting between galaxies right now, invisible save for their gravitational pull, never to merge with anything again. These ejections aren't just theoretical. Simulations show that in a chaotic black hole ménage à trois, the gravitational tug-of-war often ends with one black hole getting a powerful kick, so powerful it can escape even a galaxy's grasp. Imagine something with the mass of millions of suns being hurled through intergalactic space at thousands of kilometers per second. A ghost with no home. Even without a third wheel, not every binary merger is smooth. Some pairs come tantalizingly close but miss, what scientists call a near miss or a flyby. Their paths might bend sharply, throwing them into dramatically altered orbits, but not quite binding them together. If they're lucky, or unlucky, depending on your perspective, they may get another shot billions of years later, or they may drift apart, pulled away by the larger structures around them. One of the wildest outcomes of these chaotic encounters is the gravitational slingshot. This occurs when black holes, or stars or even spacecraft, gain speed by swinging around another object's gravitational field. In space, velocity can be stolen. In some three-body interactions, one black hole is flung outward, while the other two draw closer. Sometimes one is launched into a new orbit entirely, sometimes it's sent packing forever. These slingshots aren't rare in dynamic environments like globular clusters or galactic cores, where black holes move in dense swarms. It's a bit like watching a crowded billiards table after the break. Objects ricocheting, clustering, scattering. Except in this case, each ball weighs millions of suns, and the game takes eons to unfold. There's also the phenomenon of gravitational wave recoil. When two black holes merge, the gravitational waves they emit don't radiate perfectly symmetrically. If more energy is released in one direction, the final black hole receives a kick in the opposite direction, like the recoil of a gun. This isn't just a theoretical curiosity, it's a calculated effect of Einstein's equations. These recoil kicks can be strong enough to send the new black hole out of its host galaxy, especially in the early universe when galaxies were smaller and less massive. It's a little staggering to think about. A newly formed black hole, millions of times the mass of our sun, born in a violent merger, then flung away from its cosmic birthplace like a stone skipping across a pond. This kind of chaos isn't just background noise, it shapes the structure of the universe. When black holes are ejected, galaxies lose part of their gravitational anchors. When mergers are delayed or disrupted, the timeline of galactic evolution shifts. Black holes influence star formation, galaxy shape, even the flow of dark matter. Their fates ripple outward, and not every black hole that could merge eventually does. Some are trapped in wide orbits, slowly circling each other for trillions of years without getting close enough to spark a merger. Others are disrupted by larger-scale events, like a nearby supernova or a massive gas cloud that changes the balance of forces. There's a melancholy to it. Not every encounter becomes a union. Some just remain possibilities. Even the ones that do merge can do so in unexpected ways. Some black holes spin rapidly, others slowly. Their orientations might align or clash. These differences affect the final product, its spin, its shape, even how much energy is released during the event. Two mergers may look similar from afar, but under the hood the dynamics are wildly different. And occasionally the cosmos likes to throw in something entirely odd. Intermediate mass black holes, the elusive middle children of the black hole family. If one of these shows up in a merger scenario, it can change everything. We still don't know exactly how or where they form, and when one is involved in a merger, it can tilt the odds in strange directions. So while the idea of black hole mergers might feel smooth and cinematic, the reality is more like a sprawling, unscripted improvisation. Some end in a graceful embrace, others fizzle, stumble, or erupt into chaos. In the grand theatre of gravity, not every act follows the script, and yet that's what makes it beautiful. In the emptiest corners of the universe, where light fails and time slows, there is still drama, still tension, still the unpredictable dance of mass and momentum. Sometimes black holes find each other and emerge like clockwork. Other times, they just pass by in the dark, almost touching, never colliding. And every so often, one is sent spinning away into the eternal night, never to be seen again. Even in silence, the cosmos has its plot twists. Once upon a time, long before there were planets, people, or even galaxies as we know them, there were two stars. They were enormous, ancient, and brilliant, burning with the quiet intensity that only the most massive stars possess. They lived their lives not in bustling neighborhoods of stars, but in quiet corners of the cosmos, slowly fusing hydrogen into helium, creating light that would travel for billions of years. These stars were not ordinary. They were titans, hundreds of times the mass of our sun, and because they were so massive, their lives would be short. Massive stars burn fast and die young, and when the time came, they collapsed under their own weight, unable to hold themselves up against the crushing force of gravity. With a suddenness that defies comprehension, their outer layers exploded into space in titanic supernovae, brief flashes that could outshine an entire galaxy. But the core, the dense heart left behind, did something even stranger. It didn't stop collapsing. It kept shrinking and shrinking, folding inward beyond rescue, beyond reason, until it vanished from view entirely. And so, two black holes were born. At first they had no knowledge of each other. They were separated by light years, each one drifting in the vast darkness, wrapped in silence. Time passed, millions of years, then billions. Stars formed and died around them. Galaxies twisted and merged, and slowly, ever so slowly, the two black holes were drawn closer together. Gravity is a patient matchmaker. It doesn't rush. It nudges. It pulls. It waits. The two black holes began to spiral toward each other. At first, their dance was slow, so slow it could only be measured over eons, but with each orbit they lost a tiny bit of energy, not through heat or friction, but through the most delicate ripple imaginable, gravitational waves, tiny undulations in the very fabric of space-time, waves that spread out across the universe like the ripples left behind by a pebble dropped in a still pond. As the black holes drew closer, their dance grew faster. They circled each other in tighter and tighter loops, moving at a speed that defied the senses. The space around them warped and twisted. Time itself began to bend. If you could float nearby and watch, though you wouldn't survive it, You'd see their orbit quicken into a blur. The final seconds of their dance would flash past like lightning. And then, one day, after perhaps 100 million years of circling, the distance between them vanished. The two black holes touched, not in the way objects on Earth do, but by merging their very boundaries, their event horizons. It was not an explosion. There was no light, no sound, just the gentle fusion of two invisible things into one. At that moment, a powerful burst of gravitational waves surged outward. Not violent, but immense. A ripple in the fabric of reality moving at the speed of the light. It passed through star systems, through dust clouds, through entire galaxies, distorting space as it went, expanding, whispering, announcing that something extraordinary had just happened. Eventually that ripple reached a small blue planet. On that planet, in a quiet observatory with giant silent detectors built with lasers and mirrors, a signal was recorded. A tiny chirp, lasting less than a second, buried in a sea of noise. But it was unmistakable, the signal of two black holes becoming one. The universe had spoken, and what was left behind? A single black hole, bigger than either had been alone, spinning with the memory of their orbit, ringing faintly with leftover vibrations, like a bell still humming after it's been struck. And then, gradually, it quieted. The waves faded, the distortion settled, silence returned, but something had changed. The story of these two black holes became part of ours. We, fragile beings of carbon and curiosity, had witnessed it, not with our eyes, but with our minds, with instruments built from ideas, with questions stretched across generations. And in hearing that distant cosmic whisper, we were reminded of something grand and strange, that even in the deepest silence, the universe is always moving, always changing, always telling its stories. These two black holes had been born from stars. They had drifted through the dark alone. They had found each other, circled one another, and merged into something new. In doing so, they bent space, they stirred time, and they left behind a soft imprint, a kind of cosmic lullaby. And now you know their story. It began with light. It ended in darkness. And in between there was a dance so perfect, so distant, and so strange, that it echoes still in the gentle fabric of the cosmos. May it carry you gently to sleep. In the beginning of our journey, we asked a simple question. Can two black holes become one? And as we've drifted gently through gravity's domain, we've seen how the answer unfolds, not in a rush, but in a slow, cosmic embrace. We followed the lives of stars, their fiery births and silent deaths. We watched black holes emerge from the ashes, waiting patiently across gulfs of space and time. We watched them dance. Yes, two black holes can become one, but not with drama or fire, not with thunder or light. Instead, their union comes quietly, through spirals and soft curves, through the invisible language of gravity, written not in light, but in the very bending of space and time itself. In the end, they do not rage or cry out. Two become one, and space itself remembers the moment, whispering it across the stars. When you lie back and listen to the universe, really listen, not with your ears, but with your sense of wonder, you begin to realize just how quiet power can be. Black holes are not monsters. They are not devourers. They're reminders of gravity's patience, of nature's symmetry, of the way endings can become beginnings. We often think of black holes as the final chapter, a place where matter goes to vanish, where time stutters and light falters. But as we've seen, that isn't quite true. In merging, they don't just end. They create something new. A new black hole, yes, but also a signal, a message, a ripple that spreads through the universe. It's the universe's version of memory. That ripple might take over 1 billion years to reach us. but it carries with it the fingerprint of an event we were never meant to see. It hums across galaxies, brushes past starlight, and lands, delicately, on a laser in an observatory on a small planet circling an unremarkable star. And when we listen carefully, that whisper says, "It happened." Two black holes, once stars, once light, found each other. They spiraled together, they merged, and the universe, vast and silent, took note. In asking where in the universe this video finds you, we invited you to imagine your place in all this. Whether you're under a blanket, lying on the floor, curled up in a chair, or simply floating in thought, you're part of this quiet narrative too. The atoms that make up your body were forged in stars, shaped by gravity, recycled through cosmic time. Somewhere in your being is the memory of collisions, the echoes of ancient dances, and the stardust from long-lost galaxies. To those of you who've joined this channel, offered a like, or simply pressed play, thank you. You're part of this little space we've created, a place where science isn't loud or flashy. It's calm, curious, and, if we've done it right, just interesting enough to keep you awake until it helps you drift off. And if you're still awake now, well, maybe we've made black holes too fascinating. But perhaps that's not such a bad thing. After all, what better thought to carry into your dreams than the idea that, in the quietest corners of the cosmos, two ancient shadows once found each other? Not with noise, not with light, but with gravity, with patience, with time. And even now, long after their union, the fabric of the universe still carries their story, softly, gently, forever.